Welcome to the fifth lecture of this week. So, today we will discuss about properties of various types of laminates. First is cross ply laminate. In cross ply laminate, we know that the plies are either 0 or 90. So, plies have 0 or 90-degree orientation of fibers. Now, in such cases we know that the plies are specially orthotropic. That means, they do not have any coupling between shear and normal terms. So, QIS of any layer K is 0. So, I is equal to x or y. So, QXS and QYS both are 0. Now, so that means, when we make A matrix or B matrix or D matrix out of them, so they also have the corresponding IS terms 0. So, just for example, if I write K IS, that is K is equal to 1 to n Q IS multiplied by ZK minus ZK minus 1. So, when we sum this up, it is always 0 because QIS itself is 0. And similarly, BIS is equal to 0 and DIS is equal to 0. So, here I is equal to XS. That means, AXS is 0, AYS is 0, BX is 0, BY is 0, DX is 0 and DYS is 0. So, A matrix looks like this: AXX, AXY 0, then we have AYY 0 and then we have ASS, and that is symmetric. Similarly, B matrix would look like this: BXX, BXY 0, then we have BYY 0 and then we have BSS 0, and this is symmetric. And likewise, D matrix is also same thing, DYY 0 and DSS 0, and this is symmetric. So, in this kind of cases, there is no coupling between shear and normal terms, and similarly, there is no coupling between twisting and bending. Now, so irrespective of whatever it is, symmetric, antisymmetric, balance does not matter, A, B and D have always this XS terms or SX terms 0 for cross ply laminates. Now, let us look into symmetric laminates. Now, symmetric laminates, we know that at the symmetric locations the angles are same, the fiber orientation angles are same. So, if we look at this laminate, here we have 6 layers, and these 6 layers, if we see this, the top and bottom, the blue layers have angle theta, then these red layers have angle phi, and again these two symmetric layers have angle alpha. Now, in this kind of laminates, B matrix is 0. That means, any laminate which is a symmetric laminate, B matrix, which signifies coupling between in plane and out of plane behavior, is 0, and we will prove that. So, for proving, we will take the example of this laminate which has 6 layers. Now, if we can prove it using 6 layers, we can just extend it, and for any number of layers the same thing can be proven. So, this 6 layers laminate, let us say that Z equal to 0 is here at the junction between the third and fourth layers, that means, just at the mid layer of the mid portion of the laminate. So, here we have Z equal to 0. Now, this is layer 1, as we know layer number goes from top to bottom to top. So, 1, 2, 3, 4, 5, 6, and then at these junctions we have defined Z's. So, Z0 is Z at the bottom, and then between at the junction between the first and second layer we have Z1, Z2, Z3 lies at the Z equal to 0 line. So, Z3 is equal to 0, and it goes on. And we also assume that the thickness of the bottom layer is T1, Now, for symmetry, the thickness of the top layer has to also have to be T1. So, layer 1 thickness is T1 and that is same as the thickness of layer 6, which is T6. Similarly, here then thickness of the second layer is T2 and that should be same with the thickness of the fifth layer. So, T2 is equal to T5 and thickness of third layer is T3 and that should be same as the thickness of the fourth layer. So, T3 is equal to T4. Likewise, now if we define the Z0s in terms of these thicknesses, then Z's in terms of the thicknesses, then Z0, this the bottommost portion, the Z value here is T1 plus T2 plus T3, but with a negative sign because it is below the Z equal to 0 line. Similarly, at the topmost portion, Z6 is T1 plus T2 plus T3. Likewise, Z1 is T1 plus T2. So, Z with a negative sign. So, we can see that here, and Z5 is again T1 plus T2 with a positive sign. Z2 is just T1 with a negative sign and Z4 is T1 and Z3 that is equal to 0. So, with this now we will try to prove that B matrix is 0. Now, because thetas are same here, so Q matrix is also same. So, whatever Q matrix we have here, Q1 Q x y in the first layer should be equal to Q x y in the sixth layer. Likewise, so it should be equal to Q x y in the sixth layer. Similarly, Q x y at the layer 2 should be equal to Q x y at layer 5 and Q with respect to x y at layer 3 should be equal to Q with respect to x y at layer 4, because the materials are same, their proportions are same and angles are same. So, at these two symmetric locations Q's are same. Now, let us try to derive the B matrix. So, B matrix is nothing but summation Z equal to K equal to 1 to capital N total number of layers. So, K equal to 1 to capital N, for this particular case N equal to 6. So, K equal to 1 to N, then Q matrix with respect to x y for the kth layer multiplied by Z k square minus Z k minus 1 square by 2. Now, we can expand it and write the same thing for total 6 layers. So, let us write it for them. So, for the first layer we have Q x y 1 and then we have Z k is minus of T 1 plus T 2 and Z k minus 1, which is Z 0 is minus of T 1 plus T 2 plus T 3. Now, when we square them, the minus sign does not exist. So, T 1 plus T 2 square minus T 1 plus T 2 plus T 3 whole square divided by 2, that is for the first layer. Now, let us write it for the last layer. So, we have Q 6 multiplied by T 1 plus T 2 plus T 3 whole square minus T 1 plus T 2 whole square, and then we will write for the second layer. So, for second ply we have Q x y at k equal to 2 and then we have Z k, which is Z 3 Z 2 and Z 2 is equal to T 1 with a negative sign, but we square it. So, the negative sign does not come into picture, minus Z 1, which is T 1 plus T 2 with a negative sign, and finally, we get this, and then we have Q matrix for the fifth layer x y and for that in the same way we can write z 5 minus z 4. So, z 5 square minus z 4 square, which is equal to this by 2, and then we have Q matrix for the third layer, and for that we have 0 minus T 1 square by 2, and for the fourth layer we have T square T 1 square minus 0 by 2. Now, let us look into this fact that Q x y of the sixth layer is equal to that of first layer. Similarly, Q x y of the third layer is equal to that of fourth layer, or fourth layer is equal to that of third layer. So, this and this are same, and similarly Q x y of fifth layer is equal to that of second layer. So, this Q and this Q are same, this Q and this Q are same, and this Q and this Q are same. Now, if I add these two up, what I get is 0, because this what is here, that is just negative of this. So, on being added these two term gives me 0. Similarly, on being added these two term also gives me 0, and again after adding we get 0 here. So, finally, we get a matrix with all zeros. So, this proves that the B matrix for a symmetric laminate, irrespective of whether it is cross ply, angle ply, the B matrix is 0. That means, there is no coupling between the in plane terms and out of plane terms. So, if you want to design a structure where this kind of coupling is not desired, then we can go for a symmetric layout. Now, many a times, especially when we want to do shape adaptive design or tailoring of some properties, then sometimes we desire this B matrix to be present. That means, we want the coupling between in plane and out of plane behavior to be there, especially for some kind of thermal designing something shape adaptive under thermal behavior. Many times we want this kind of couplings. So, under the effect of temperature with some boundary conditions, we see bending, and if you want to arrest that bending or reduce that bending, then this kind of coupling can be helpful. And again, if these symmetric laminates are cross ply, then apart from B matrix being 0, we will have AXS, AYS and DXS, DYS 0 as well. Now, let us look at balanced laminate. Balanced laminate, as we have seen, number of theta and number of minus theta are same. So, this is an example of a balanced laminate. Again, we will take 6 plies, and again it can be extended to any number of plies. So, here what we can see, this blue layer, these two blue plies are opposite of each other, theta and minus theta. Similarly, these two reds are phi and minus phi, and these two blacks are alpha and minus alpha. The T's are again same, but here we have to have those plies with same color here, or same magnitude of theta with same thickness. So, for example, here this blue ply is balanced by this blue ply. So, we have T 1 is equal to T 4. Similarly, this red ply, that the thickness is T 2, and it is balanced by the another red ply with minus phi. So, that is T 2 and T 5 are same. Similarly, T 1, T 3 and T 6 are same, and Z's are defined in this way. Now, we will go to balanced laminates. Now, in balanced laminates, we know that number of plies with orientation theta should be same as the number of plies with orientation minus theta. So, for example, here we see a blue layer or blue coded layer which has angle theta, and then we have another blue layer which is of angle minus theta. Similarly, a red one with phi and another red one with minus phi, and a black with alpha, another black with minus alpha. Now, their thickness of these two corresponding ply have to be same. So, this ply is balanced by this ply. So, their thickness has to be same, that is why you have T1 is equal to T4. Similarly, this red ply is balanced by this red ply. So, their angle have to be same. So, we have T2 is equal to T5 and this black has to be balanced by this black. So, T3 is equal to T6. Now, here accordingly we have to define the Z's. Again we have Z3 is equal to 0 and rest of the Z's have value accordingly. For example, Z2 is equal to T3 and similarly Z minus T3. Similarly, this Z2 is equal to minus T3 minus T2 and again last one is minus T3 minus T2 minus T1. But here we cannot say that Z2 and Z4 have to be same with negative sign, because the plies are not stacked in that way. So, Z2 can have a value other than a negative of Z4, unlike the previous case. Now, in this kind of laminates, AXS and AYS are 0. So, in this kind of laminates, AXS and AYS are 0, and since this is symmetric, this is equal to ASX and ASY also. So, that quantity is 0. Now, to prove that, let us look into the fact that layer 1, in layer 1 we have QXS of layer 1. So, we can call it QIS with I going from X and Y. So, QIS, whatever QIS we have for layer 1, that should be negative of the QIS of layer 1, 2, 3, 4, layer 4, because these two plies have opposite angle of orientation, and we have seen that QXS and QYS, which we are calling as QIS, are odd functions of m and n. So, when odd functions of theta. So, when theta changes its sign, these two quantities changes their sign also, but other quantities like QXX, QXY and QYY, they are even function of theta. That means, when theta changes their angle, those values remain same. Now, because of this, we will see that the AIS becomes 0. So, AIS is 0. So, for that let us write the expression for AIS. AIS is equal to summation k is equal to 1 to n. We have QIS of the layer k is equal to ZK minus ZK minus 1. Now, ZK minus ZK minus 1 is nothing but the thickness of that layer. For example, if I have the first layer, ZK minus 1 means Z1 minus Z0. Similarly, if I am in the second layer, ZK minus Z1 means ZK minus ZK minus 1 means Z2 minus Z1. So, they denote nothing but the thickness of that respective layer or respective ply. So, if we do that now, we can just expand this up. So, we can write QIS of first layer multiplied by thickness of the first layer, plus we have QIS of the second layer multiplied by the thickness of the second layer, plus QIS of third layer multiplied by the thickness of the third layer. Then we have QIS of fourth layer multiplied by thickness of the fourth layer, plus QIS of fifth layer multiplied by the thickness of the fifth layer, and then QIS of sixth layer multiplied by the thickness of the sixth layer. Now, let us look at these two blue layers which balance each other. So, first and fourth. So, is of 1 is equal to q is of 4. So, and sorry equal to minus q is of 4, and T 4 and T 1 are same. So, this quantity can be written as minus of q is of 1 into T 1, because q is are just opposite of each other and thickness are same. So, on being added, these two quantity would give us 0. Similarly, if I look at second and fifth layer, this layer and this layer, they also shows us the same thing. T 2 is equal to T 5, T 2 and T 5 are same, but q i's are opposite of each other. So, again on being added, they will give us 0. And similarly, if I take the contribution from first layer and if I take the contribution from third layer and sixth layer, that also adds up to 0. So, finally, this quantity becomes 0. Now, as we have seen that in A matrix, the position of the plies does not matter, because finally it is the thickness, it is only those plies that matter. So, that is why AIS finally adds up to 0. But if we want to do the same thing for DIS, that will not be the case, because although the QIS are opposite of these two balancing plies, but because their positions are not symmetric, that is why the contribution from ZK cube minus ZK minus 1 cube will not be negative of each other. So, that is why DIS is not 0 and BIS is also not 0. So, in balanced laminate we have AIX equal to 0. So, for a balanced laminate, A is equal to AXX, AXY 0, AXY, AYY 0, and 0 0 we have ASS. Now, here only these terms, that means IS terms, were opposite of each other when theta goes from positive to negative, but the QXX, QYY, QXY and QSS, they do not change their value, they do not become negative. So, the QXX of this ply is same as QXX of this ply. That is why if you add up their contribution, they are additive, they do not cancel each other. That is why these quantities does not become 0, rather they get doubled from the contribution of two plies, whether these quantities become 0 because of the corresponding Q terms are opposite for each two balancing ply. Now, again if this is a if this is a balanced cross ply laminate, that means 0-90 sequence, then anyway A matrix is 0 and the AXS and AYS are 0, and we know that BXS, BYS and DXS and DYS are always 0. Now, let us look at antisymmetric laminate. Now, antisymmetric laminates are also balanced, but here the opposite plies are positions at the symmetric locations. So, here we can see these two blues are placed symmetrically. In the previous case, the blue was placed here, but here we have placed at the top, so that they take the positions which are symmetric with respect to the midline. Similarly, the red ones are placed symmetrically and the blue ones are placed symmetrically. Now, when this happens, the DXS and DYS also become 0. Now, symmetric laminate is also balanced, antisymmetric laminates is also a balanced laminate, all the antisymmetric laminates are balanced, but it is not the other way. We have seen that. Now, because it is balanced, so we have AIS equal to 0, where I goes from x to y. So, now we have to prove that DIS is also 0. So, now let us look at write the expression for DIS. So, DIS is summation k going from 1 to n, then we have QIS of the kth layer multiplied by ZK cube minus ZK minus 1 cube, and then we divide this by 3. Then if I expand that, we have QIS of the first layer multiplied by Z1 cube minus Z0 cube by 3, plus we have QIS of the second layer multiplied by Z2 cube minus Z1 cube by 3. Then we have QIS for the third layer multiplied by Z3 cube minus Z2 cube by 3, and we can keep writing up to ply number 6. Now, let us put the value of those thicknesses. Again, like the symmetric case, because the plies are placed symmetrically. So, they are the thickness of these two plies which are placed at the symmetric locations are same. So, we can write again the same thing, Z0 is equal to minus T1 minus of T1 plus T2 plus T3, which is just opposite of Z6. Similarly, Z1 is equal to minus T1 plus T2, which is just opposite of Z5. Similarly, Z2 is equal to minus T1 and Z4 is equal to T1 and Z3 is equal to 0. Now, let us just put these values. So, if we do that, we have QIS of the first layer, then we multiply that with minus of this cube, that means the minus sign is retained here. So, we have minus of T1 plus T2 plus T3 whole cube, then minus Z. Okay, so, we should write Z1 first. So, Z1 cube, which means minus of T1 plus T2 cube. So, we have minus of T1 plus T2 cube, and then we subtract the cube of this. Again, when we cube it, this negative sign is retained. So, negative and negative makes it positive. So, we have T1 plus T2 plus T3 whole cube and then divided by 3. Now, let us write it for the sixth layer. So, we have QIS for the sixth layer. For the sixth layer, we have this one at the top. So, we have T1 plus T2 plus T3 whole cube and minus T1 plus T2 whole cube divided by 3. Similarly, we have for the second layer. For the second layer, we write minus of T1 cube plus T1 plus T2 cube by 3, and for the fifth layer we have QIS of 5 multiplied by T1 plus T2 cube minus T1 cube by 3, and then we have QIS for the third layer, and for third layer we have again 0 minus T1 cube by 3, and here we have QIS for the fourth layer, which is T1 cube minus 0 by 3. Now, if we look here, we see that this term that comes from the thickness, they are same and of same sign, but QIS and of 1 and QIS of 6 are opposite of each other, because theta is opposite here. So, this quantity QIS, as we know, is minus of QIS of 1. So, if that is the case, then this and this cancels each other. Similarly, this and this cancels each other, and this cancels each other. So, for this ply, again if we keep it noted, we have QIS 1 is equal to minus QIS 6, because they are of opposite angle, and similarly we have QIS 2 is equal to minus QIS 5, and then we have QIS 3 is equal to minus QIS of 4. So, that is why if we sum up it becomes 0, that becomes 0. So, finally, the D matrix would look like this. In this case, D matrix is dxx, dxy 0, dxy, dyy 0 and 0 0 dss. Again, because the other components of q, qxx, qxy, qyy, qss, they do not change their sign when theta goes from plus to minus. So, because of that, the corresponding quantities in the D matrix dxx, dxy, dyy, dss, they do not become 0, rather their contributions get added up. But because the is terms are opposite of each other, so these two plies, I mean their corresponding is terms for the D matrix cancels each other, and finally this term becomes 0. So, in an antisymmetric laminate, AIS is 0 because it is balanced, and DIS is also 0. Now, if we talk about antisymmetric plies which are also cross ply. So, for that we get some more features. Antisymmetric cross ply. Now, in an antisymmetric cross ply, apart from whatever we have seen for A and D matrix, we also have Bxx is equal to minus of Byy or Byy is equal to minus of Bxx. So, to prove that, here what we have is again for that same laminate same ply, if we see Q xx of. So, let us now look at a antisymmetric ply, antisymmetric cross ply with some example, then it will be easier for understanding. Let us say we have an antisymmetric cross ply laminate which is made of just 4 layers. So, here we have 90 and here we have 0 degree, and say here we have 0 degree and here we have 90 degree, and this is z equal to 0, and suppose the thickness here is T1, T2. So, accordingly the thickness is T2 and accordingly thickness is T1, and this line is Z1 which is minus of T2 and this line is Z0 which is minus of T1 plus T2, and this is Z3, and likewise Z4 is T2 and Z. So, this is Z2 and this is Z3 and Z4 is T1 plus T2. Now, if we want to look at this, so Q xx of a 0 degree ply is same as QYY of a 90 degree ply. So, if we have a 0 degree ply, that means the fibers are oriented in this direction. For a 90 degree ply, the fibers are oriented in this direction. Now, because these are same materials and same proportions, So, whatever q I find in the fiber direction, that should be same here and here. So, in this case axis x is aligned with axis 1. So, x and this is also 1 and this is y and this is also 2, and for this case this is x which is coinciding with axis 2 and this is 1 which is coinciding with axis 1. So, in the first case x axis coincides with axis 1. So, q x x is equal to q 1 1. In the second case x axis aligns with axis 2. So, q x x is equal to q y y is equal to q 1 1 here. Similarly, q y y for 0 degree ply, that means q along this direction, that is the 2 direction. So, that is equal to q 2 2, and similarly that is q x x for a 0 degree for a 90 degree ply, which is again q 2 2. And we can verify that just by putting the transformation relations also. If I put m is equal to cosine 90 degree and n is equal to sin 90 degree, and if we put the if we use the transformation relation, then we see that after 90 degree transformation just q x and q y interchange their position. So, with that now let us try to see what happens to this b x x and b y y. So, for this ply b x x becomes summation k is equal to 1 to n. In this case we have n is equal to 4 here. So, k is equal to 1 to n, and then we have q x x of the kth layer multiplied by z k square minus z k 1 minus 1 square by 2, and then let us expand that. If we expand that, what we get here is q. So, for the bottommost layer is the 90 degree layer. So, q x x of 90 degree layer multiplied by z k square minus z k minus 1 square. So, we have t 2 square minus t plus 2 square divided by 2, plus we have k x x of a 0 degree layer multiplied by 0 minus t 2 square by 2, and then we have plus q x x of the 90 degree layer multiplied by t 2 square minus 0 by 2, and then we have q x x of a 0 degree layer multiplied by t 1 plus t 2 square minus t 2 square divided by 2. So, in that case in place of k we are just writing the corresponding fiber orientation angle. So, here instead of q 1 we have written q 90 degree, and similarly q 60 degree, q 0 degree, and so on. Now, if we find out b y y, then that is again k is equal to 1 to n q y y of the kth layer multiplied by z k square minus z k minus 1 square by 2, and then here we have q y y of a 90 degree layer multiplied by we have t 2 square minus t 1 plus t 2 whole square by 2, plus we have k y y of a 0 degree layer multiplied by 0 minus t 2 square by 2, plus we have q y y of a 90 degree layer multiplied by t 2 square minus 0 by 2, plus we have q y y of a 0 degree layer multiplied by t 1 plus t 2 square minus T2 square by 2. Now, let us compare this expression for Bxx and Byy. So, what we see here is if we write everything with respect to xx, then this quantity Qyy, we have seen that Qyy of a 90 degree layer is equal to Qxx of a 0 degree layer. So, this is Qxx of 0 degree layer, and Qyy of a 90 degree 0 degree layer is equal to Qxx of a 90 degree layer. And similarly, Qyy of a 0 degree layer is equal to Qxx of a 90 degree layer is equal to Qxx of a 0 degree layer, and likewise Qyy of a 0 degree layer is equal to Qxx of a 90 degree layer. Now, if we compare what we see here and what we see here, then we see that these two expressions are just opposite of each other. For example, here we have Qxx of 0 multiplied by this quantity T2 square minus T1 minus T2 whole square by 0, and here we have Qxx of 0 and just opposite of this sitting here multiplied with this, and likewise if we just compare term by term, we see that this is just opposite. So, this brings us to the conclusion that Byy is equal to minus Bxx. So, in a laminate which is cross ply and antisymmetric, we have these quantities as Bxx and Byy are just opposite of each other, and Bss would also be 0 for this kind of plies. Now, because this is anyway this matrix is, if we just add this, I mean the reason that because Bss is 0 is Bss whatever we find here, I mean QSS whatever is here, the same QSS is here. So, if I just add their contribution, because of the opposite nature of the thickness square terms, they cancel each other, and same thing happens here and here. So, Bss is also 0, and due to the same logic these two quantities are also 0, and it is balanced anyway. So, these terms are 0 and it is cross ply. So, these terms are also 0. Now, let us look at antisymmetric angle ply laminate. In antisymmetric angle ply laminate, what we find is its B matrix has a different nature. In its B matrix we have 0 0, and then we have Bxs, Bys 0, Bxs and Bys. Now, for that again let us again look at a simpler laminate with just 4 layers. So, let us say we have theta here, minus theta here, and we have phi here and minus phi here. So, what we can see is that QIS and QIS are opposite of each other, and when we find out the B matrix, the thickness square terms whatever is here is just opposite here. So, this is also opposite and thickness square terms are also opposite. That means, effectively they becomes additive here. Just to look at to see that, again let us define here Z1 is equal to minus T1 plus T2, and Z0 is equal to minus Z1 is equal to minus T2 and Z0 is equal to minus T1 plus T2. So, minus of T1 plus T2 and this is equal to Z2 and again Z3 is equal to T2 and Z4 is equal to T1 plus T2. Now, if we look at any of these terms, so suppose Bxx, for Bxx the expression is summation of k is equal to 1 to n and then we have Qxx of k multiplied by zk square minus zk minus square k minus 1 square by 2 and then if we add it up it becomes kxx of 1 multiplied by t square minus T1 plus T2 whole square by 2 and then we have Qxx from the second layer and that we have 0 minus T2 square by 2. From the third layer we have T2 square minus 0 by 2 and from the fourth layer we have T1 plus T2 square minus T2 square by 2. Now, this quantity is equal to Qxx of 1 because even if the angle becomes opposite, the Qxx, Qyy and Qss and Qxy they are same and similarly this quantity is Qxx of 2. Now, we can see that this term related to thickness and this term they are opposite of each other. Similarly, this and this they are opposite of each other. So, on being added it gives us 0 and similarly we have Byy is equal to Byy is equal to Byy is equal to Bxy is equal to Bss that is equal to 0. But Qis for I would say layer 1 is negative of Qis of layer 4 and Qis of layer 2 is negative of Qis of layer 3 where I is either x or y. So, because of that when we find out the corresponding term in the B matrix, they does not become 0, rather they add themselves up and this quantity finally becomes non-zero. So, with an antisymmetric angle ply laminate we have B matrix with most of the entries populated to be 0 except for these IS or SI terms. Now, in antisymmetric laminate in general we have seen that we can get rid of the bending the twisting and bending coupling, that means dxs and dys terms are 0. Now, sometimes we desire such type of couplings, in that case we do not go for an antisymmetric laminate. One example is aeroelastic tailoring. So, when we want to do aeroelastic tailoring we sometimes want the coupling between and bending and extension modes, and in that kind of cases we to ensure the desired coupling we try to adjust the lamination sequence in such a way that that level of coupling exists between those two modes. So, what we have seen here today is that using various types of symmetry or antisymmetry, cross ply, angle ply, sometimes we impart some kind of coupling and sometimes we avoid some type few types of couplings. So, that helps us designing a composite structure the way we want it. So, this so that is why these conclusions are quite useful when we want to design a composite structure. So, with that I would like to end this lecture here. Thank you.